Welcome to the office. We want to take a look at an example today of classifying a factor group according to the fundamental theorem of finitely generated abelian groups. And this example should look a little bit familiar to some examples that we've already seen. Of course, if this were a 1 right here, life would be great. Everything would be so easy, right? We would just use that previous theorem that we had considered, and we would be all set, right? It just kind of eliminates this guy and it's isomorphic to this. Unfortunately, that's not what we have. So we say, oh, darn. Now, we looked at a different example that had just 2 entries and looked kind of like this. And you say, okay, well, that gave us something a little bit different. And we could use those same methods that we used previously, but I would like to share just a slightly different method for us. And that's actually just by use of a homomorphism. So consider phi a homomorphism from Z3 direct product with Z direct product with Z, and map that to, let's see here, Z3. I want that to stay the same. Direct product with Z, have that stay the same. Direct product with Z5. Excellent. So if I were to consider this defined by phi of, so I want to write this as phi of A, B, C is equal to A, B, right? So whatever I enter here stays the same. Whatever I enter here stays the same. And the last entry, I'm just going to go ahead and take that and have it be a quotient or a remainder of C when considering the division algorithm dividing by 5. All right, so where RC5 is the remainder in the division algorithm when dividing C by 5. All right, cool. Then the kernel of phi is equal to, so the only way I'm going to get 0, 0 something is, of course, so this is the set of elements 0, 0. Now here I can take anything that is a multiple of 5. So 5k, let's call it, where k is an integer. Now, if we want to be as formal as possible, we want to recognize that this is equal to 5 times 0, 0. I'm sorry, not 5 times that, but k times 0, 0, 5. Let's see here. Yep, excellent. Where k is an integer. But what's the benefit of that perspective? Well, taking that perspective allows us to recognize that this is exactly the subgroup that's generated by 0, 0, 5. So 0, 0, 5. Excellent. So now I have a homomorphism. I have not verified that it's a homomorphism. I would encourage you to do so. But I have a homomorphism from here to here, whose kernel is exactly that. We also have that phi is onto. Okay, we know that this produces an isomorphism, or induces isomorphism, where the quotient group Z3 direct product with Z direct product with Z quotient by what's generated by 0, 0, 5 is isomorphic to the image of phi, right? The image of this under phi. But since it's onto, we actually get that it's isomorphic to the entire codomain here, Z3 direct product with Z, direct product with Z5. So sometimes it's most convenient to simply create a homomorphism that has the desired kernel and the desired codomain to show that the quotient group is isomorphic to that codomain, and life is good, right? So that's all that we wanted for this example. That gives us exactly what we're looking for. In the coming videos, we're going to take a look at some more theorems, definitions, followed by a few examples. So thank you for your time. I'll see you guys back in the office in just a little bit.